All right, it's reaction time. We're going to be looking for evidence of chemical reactions. So here we go. Let's do this. Question, is it a chemical reaction? If you change something in size, for instance, tearing it up or cutting it in half, not a chemical reaction going on there. A change in shape, if it goes from flat to a round or a ball shape, it just it doesn't actually change the chemistry of the object. It's changing the shape. What we're talking about here are not chemical reactions, but physical changes. In the same way, changing the phase of an object. So for instance, if you're boiling water or melting ice, it's still staying the same stuff. Water is just turning into water in a different phase, a different state of matter. So melting water, evaporating water, or melting ice, sorry, evaporating water, any of these phase changes are simply physical changes. How about a mixture? If you mix together ingredients, say like flour and sugar and salt and chocolate chips or whatever, if you're making cookies, that's simply a mixture. Same thing with the Chex Mix, for instance. These are just mixtures. They're just items that are all mixed together. They're not actually chemically changing at all. They're just sitting next to each other, and they could easily be picked apart really into their individual components again. And a solution, if you say dissolve some sugar or dissolve some salt in some water, or food coloring in water, for instance, is just a solution. And that is just pretty easy to recover. You can distill that and get the salt or the sugar back. It's just a solution. There's no chemical reaction going on. It's simply a physical change. So how do you get a chemical reaction? I mean, after all, this is reaction time. This unit is called reaction time. Well, let's, in class, we did a quick mini reaction here, and we looked at different types of glassware. First of all, the beaker, the Erlenmeyer flask, and the graduated cylinder. And this one here is the Erlenmeyer flask. It's got a little narrower at the top. The beaker, of course, is more just a round cup-looking thing. And a graduated cylinder is a very tall, skinny tower that's marked with very specific markings, like this one here. And when you go to measure a liquid, what you're looking for here is liquids tend to have a little bit of a bubble to them like this. The surface tension keeps them sticking to the sides a bit more than in the middle. And so you've got to look for what's called the meniscus, which is this curve here. And where you measure that is right there at the bottom of the curve. So the 20 line, which is this longest line here, that's 20 milliliters right here of this liquid. It's not here or here that you measure right at the bottom to be very accurate. All right, so in class we observed with various senses, and we combined acetic acid, which is vinegar, with sodium bicarbonate, also known as baking soda. That's right, sodium bicarb, as it's called in the business. And we combined those, and we saw all kinds of stuff going on. In fact, we saw things like gas bubbles, as you would imagine. Is that a sure sign of a chemical reaction? Well, it's a pretty good indication, but not necessarily a given. Just because you see gas bubbles does not necessarily mean it's a chemical reaction. Think about when water boils. It's a physical change. It does have gas bubbles, but it's a pretty good indication. Here is water being separated into two different components. And maybe this is a chemical reaction. We'll get to that in a minute. So you've got some evidence here, but not necessarily proof. How about a color change? If you mix two things together and you get a color change, like we did in our sample reaction in class, it's a pretty good indication. But again, when you put, say, food coloring into water, that's a color change, but it's simply a physical change. So a color change, again, pretty good evidence, but not necessarily definite proof. When something precipitates out of something else, so like precipitation falls from the sky, in chemistry we generally refer to this as the precipitate, which is the solid little chunks of things that would settle out of a liquid. And that's usually a pretty good indication that you've got something new formed here, and it's a pretty good indication of a chemical reaction. But again, it's not necessarily proof. Finally, energy being released or used up. So for instance, the classic combustion in the bottle that we've done, that's obviously some serious energy being released. Or in this case, sometimes we have energy being used up in other chemical reactions. These here are all pretty good evidence that the chemical reaction is occurring, a good clue. But the real proof, if you really want to have proof of a chemical reaction, in other words, a sure sign of a chemical reaction, you've got to look for this: formation of a new substance with new properties. In other words, you've got to make something new, some new compounds out of the atoms that you have broken apart and rearranged into something new, and it has new properties. So let's take a look at some examples of what this might be. Is this an example of a new substance with new properties? Is this a chemical reaction? Boiling water. Well, you're starting out with water, and you're ending up with water. It's just in a vapor form. So you're starting with H2O and ending with H2O. This is not a new substance with new properties. This is not a chemical reaction. On the other hand, if you take water, for instance, like we did in class a while back, and you separate it into two separate gases, in other words, you break apart the water molecules, you take water and you separate it into hydrogen and oxygen, you're taking the hydrogen and splitting it apart from the oxygen and creating two new substances, hydrogen molecules and oxygen molecules. And what you have here are two very different substances with two very different properties from water. Water is a clear liquid that you can drink. Hydrogen is a flammable gas. And oxygen is another clear gas that supports combustion and you can breathe. So obviously two very different things if you split water actually in half. So this is definitely a chemical reaction. The other example, of course, was the vinegar and baking soda, the acetic acid and sodium bicarb. And when you put those together, you actually get not just bubbles and all that, but you get three new substances. Sodium acetate, which is formed and settles to the bottom of the beaker, water, and carbon dioxide is given off. So what does that look like at a chemical level? If you look at the actual molecules, and here are some representations of what those might look like if we just drew atoms as simple spheres like this. Here's acetic acid, it looks like this. Here's sodium bicarbonate. Here's sodium acetate. Here's water, this makes sense, right? Two hydrogens, those are the white spheres, and one oxygen. And here's carbon dioxide, two oxygens and one carbon. So these are kind of what these molecules would look like. And if you look very carefully at these here, and you go, okay, first of all, we've got the reactants, which are the ingredients. These are the two ingredients that we put together that react, so we call them the reactants. And these over here is what is produced in the chemical reaction. So these are what are called the products, the reactants and the products. And if we compare the reactants to the products, we find that they should have the exact same number of atoms. So for instance, if we look at the oxygen atoms, here are two oxygen atoms. They're represented with the red spheres. 1, 2, 3, 4, 5 oxygen atoms in the reactants. So 5 over here, and how many are over here in the products? 5 oxygen atoms in the products. And if you go through and look carefully at the numbers of all of these different things, so carbon, for instance, 1, 2, 3 carbons over here in the reactants. There should be 1, 2, 3 carbons, which are the dark gray ones here, in the products. And carefully looking through each of these, adding up all of the hydrogens, for instance, there's 5 hydrogens in the reactants, 1, 2, 3 hydrogen, 4, 5 hydrogens in the products. So all of these things, each atom from over here is simply broken apart from its molecule and rearranged and reassembled into something else over here. The matter is not disappearing, it's not being created anywhere, it's simply getting rearranged and becoming something different, a new substance with new properties. So other examples, of course, when we burn magnesium, and we take the reactants here, we've got magnesium and oxygen in the air. Those combine and form the following product, magnesium oxide. All right, and that's that white powdery ash that is formed afterwards. And we can use that for something completely different than magnesium and oxygen would be used for. Magnesium is a magnetic, it's a metal, it's magnetic, it conducts electricity. Magnesium oxide is kind of this powdery ash looking stuff, and it doesn't conduct electricity or magnet. It's not magnet. It's nothing like these two reactants. It's a totally new product. Totally new. Now, when we write these things out, chemists are a little bit lazy and efficient, I guess you would say. And we write out their actual chemical formulas. So we would say Mg for magnesium plus oxygen, and it's usually found as a molecule with 2 oxygen atoms stuck together. So we had Mg plus O2 would give you magnesium oxide, which we would write as MgO. Now, if you look carefully at this, you'd realize that this is not a balanced equation. Magnesium, there's one of them over here and one of them over here. But oxygen, there's 2 oxygens there and only 1 there. So this needs some balancing work. And we're not going to do that right now. We'll get to that a little bit later on how to balance these equations. But this is just the general, a general start on what the reactants and the products are written out in chemical formula form. One of the reactions we did in class here was to take sugar and combine it with highly concentrated sulfuric acid, which is extremely dangerous and nasty stuff. And what we find is sugar itself, sucrose anyway, is made up of carbon, hydrogen, and oxygen in the following ratio, C12, H22, O11. And sulfuric acid, of course, H2SO4. And what happens when you put these together is you get a serious reaction occurring, and it creates this snake-looking thing that comes out of the beaker and creates a heck of a lot of heat as well. So you've got a color change, you've got bubbles forming, you've got gas given off, but the clue that this is definitely a chemical reaction is the fact that you have some new substances. Here you have steam, this is actually water in the air, and this big chunk of something here is a completely new substance with new properties. It is not sugar, it is not sulfuric acid. You've got some new stuff coming out over here. So what is it? Well, here's the deal. If you take all of these atoms here that make up a sugar molecule and you break them apart and rearrange them, well, you can make 11 water molecules, H2O. Look at that. You can take these atoms and rearrange them into 11 separate water molecules, which leaves you with a bunch of carbon. So what you have is carbon, and that's what that big black chunk of nasty stuff is carbon, and water, which is burned off, or which is boiled off in the heat from the reaction. And then you're actually left over with some sulfuric acid that's not actually used in the reaction. So again, what you've got here is new substances, new properties, and a nice little pile of carbon there, which is what you are, a pile of carbon. And me too, we're carbon-based life forms. So the reactants produce the products as they undergo a chemical reaction. So how can you be absolutely sure that a chemical reaction has happened? There's only one way. The proof is, how? Formation of a new substance with new properties. In other words, the atoms are simply getting rearranged into new compounds that have different properties than the original reactants. Which leads us to one of the most important concepts in chemistry is the law of conservation of mass. In other words, what this means is mass is conserved. Conserved means to save. You conserve something, you're saving it. So you are saving the mass from the reactants over here and rearranging that into the products. It should have the exact same mass because it's made of the exact same atoms just rearranged. So what is the law of conservation of mass? Matter, in other words mass, matter can be neither created nor destroyed. Atoms just get rearranged.